0.3 kilometres. So I've done tests where you run the model with different vertical extents, and the top boundary condition is not affecting the results. You know, if I put the top boundary condition down here, then I get essentially the same flow.
One more thing I want to say is, recently some people are arguing whether, supergradient wind even in a free atmosphere, so around the eyeball regions. So do you think it impacts on your results or not? I mean, some supergradient wind can be found along the eyeball regions, even in 5 to 10 kilometers. Yeah. So
I think the mechanism for the supergradient flow on the inner edge of the eyewall up there is different to what it is in the boundary layer, and I don't think it affects the results here. But those simulations, which I think this was the paper by Darling Zhang.
Yeah, and also Brian and working on Skinner simplified.
Oh yes, yes. Those, I don't remember the Brian and Rotuno, but Darling Zhang's paper, there was basically a layer, there was the supergradient flow in the boundary layer, and then there was a layer that was close to gradient balance, and then from about 5 kilometres upwards, there was a second layer of supergradient flow. Yeah, so I don't think that upper layer of supergradient flow directly affects the boundary layer. Okay.
Maybe I missed what you said, but is the particle diffusion coefficient constant or not?
In this particular simulation, it's not constant. In this simulation, I was using a first order closure, a Louis scheme, as is used in a lot of NWP systems. So that's a good question. In the Louis scheme, the diffusivity is proportional to the wind shear and multiplied by the square of the mixing length. And the mixing length, the mixing length looks like Kepert does it near the surface, and then it goes smoothly to the constant value of, I think I was using 80 metres for this run. So it's using a flatted up formula for mixing length. But I have also I've used a Meli-Yamada level 2.5 scheme, and which produces almost identical results. When I first did the work, I was using the Meli-Yamada scheme. When I discovered the Louis scheme produced almost the same results, I stopped using the higher order closure because it's more expensive and it's less stable numerically. I've also can run the model with K constant with height, which has some effect on the wind structure. I've got a KPP type scheme like the Monash University scheme coded up in there as well. The results are not, they're a bit sensitive to the boundary layer scheme, but the broad features of inflow, outflow, supergradient flow, maximum updraft occur basically with any scheme.
I have a short question. Is this steady computation? Or you give some initial field from typical observation data and doing the forensics?
I begin the simulation with the flow is just the gradient flow for the pressure field, and I run them out for 24 hours, which is more than enough to get to a nearly steady state.
Okay, so this is steady and equilibrium.
Yes.
Steady.
Yeah. It's a good question, and we might come back to that to sort of just justify why that's steady state tomorrow, because that's important to some of the very recent work. So just to remind you, here are the observations from Zhunjiang, and they look quite similar. We have the outflow, the inflow, the maximum winds and so forth. So the model is matching the mean observations. Another comparison to the observations, so these were the Michael Bell's work, and again, in structure at least, we're quite similar. One of the diagrams I quite like to use, and I'll introduce it to you because you'll see some more of this type of diagram, it sort of summarises everything in a single figure. The red curve is the gradient wind, so this is radius and this is wind speed, so the red curve is the gradient wind. The blue curve is the azimuthal surface wind. The green curve is the negative of the surface radial wind, so this is the inflow component. And you can see that that increases up towards the radius of maximum winds and then declines, very much as in the Souter's observations. Magenta is the vertical velocity, which is at 1 kilometre height, and that's been multiplied by 100. So we're seeing about half a metre a second of ascent there. And the other one, which I've started putting on these diagrams recently, and we'll see the reason for this tomorrow, is the vorticity of the gradient wind, and that's showing a typical cyclone structure of strong vorticity in the low wall, and then a narrow skirt of vorticity at large radius. The skirt is also an important feature that has been shown to be present from observations by Malin et al. In about 2005. But it's quite a good summary of these three panels because it picks up the radial variation of these things and also the location of the updraft. The location of the updraft, you can see, is slightly, in this case, is slightly inside of the radius of maximum winds, and that usually occurs with the with this model. The distance inside is something that we'll talk a little bit about later on.
Excuse me. There are two peaks in the vertical motion. One is the deepest one. The
There's this little peak here.
Yeah.
Good question. I think what it probably is, I'm not actually sure. It is there quite often. I think what it probably is we have essentially zero vorticity gradient there, and I think we're getting a weak wave motion forming on that, inside that eye. It could also be numerical because the model is coded on a Cartesian grid, and we've got very tightly curved flow, so it's possibly a numerical artifact. One of the things I will do one day is write another version of the model in cylindrical coordinates and see if this goes away. I don't think that is a realistic feature.
What is the resolution of the horizontal?
These simulations were 3 kilometres high resolution, which is, if you want to resolve, people now run models of finer resolution than that, but there's really no point because the gradient wind field is quite smooth, so there's no point in going finer.
May I have a question?
Yes?
If you look at the radial vorticity profile, I can see the radial vorticity outside the RMW is not equal to 0. So this means the model assuming, not assuming the Rankine vortex, but Rankine with skirt vortex.
It's a Rankine with skirt vortex, that is correct. I have run the model with a true Rankine vortex. The results are quite the results are somewhat different. When you have a true Rankine vortex, the inflow becomes much stronger. The supergradient flow at the eyeball becomes much stronger. And remind me to explain to you why in about 3 slides' time, because it's an important feature of the overall dynamics of the boundary layer. Yes. Any more questions? This is the same simulation again, except plotted slightly differently. So the black contours are the azimuthal flow. We've got the pink arrows again showing the radial vertical flow vectors, but this time the colour shading is the supergradient flow. So it's V minus VGR, and the white contour is the zero contour of that field. And so what we're seeing here is this large area of supergradient flow in the upper part of the inflow layer and lower part of the outflow layer. As we get in towards the radius of maximum winds, that becomes 2 or 3 metres per second supergradient. So in this particular simulation, it's about 5% supergradient. These bands here, I think they're connected with the oscillations of the vertical motion, and I'm not sure whether those are actually a realistic feature of the model. The other thing that's quite interesting is when we get further up, it goes back to being weakly subgradient, only fractionally so, but that's quite a consistent feature of the model. Sometimes the extent to which it's supergradient, that can vary from being just 1 or 2% to as much as 15 to 20%, depending on the structure of the storm. And as we noticed with the observations, we are still, the strongest supergradient flow is still clearly within a region of inflow. So it's simple to understand why we might get supergradient flow, at least to a first order. The flow in the upper part of the boundary layer, it's towards the top of the boundary layer, so it's not quite conserving angular momentum, but the dissipation of angular momentum in the upper boundary layer is relatively weak. And so if we have strong inflow, it's by conservation of angular momentum, you'll tend to spin up a wind maximum. That's a very simple argument, and you can sit on a swivel chair and give yourself a kick and turn around and pull your arms in and you spin faster, or you can watch an ice skater, and people know that this produces strong rotation. The problem is that the supergradient flow in this model is steady, and normally if you have supergradient flow, you get an outwards acceleration associated with it. The flow is supergradient. That means that the centrifugal force and the Coriolis force, which are directed outwards, are stronger than the pressure gradient force, which is directed inwards. So what would normally happen with that supergradient flow is you get an outwards acceleration and the flow should start moving out. And as the flow moves outwards, of course, conservation of angular momentum, it's going to slow down. So the key to understanding the supergradient flow is that the jet maximum, the supergradient flow maximum, occurs within the inflow layer. Because it's supergradient, there is an outwards acceleration. So how do you manage to maintain inflow in the presence of that outward acceleration? Because if you didn't maintain the inflow, you're going to lose the supergradient flow. It's essentially going to be a rotating version of geostrophic adjustment, where in geostrophic flow, if you have flow that's super geostrophic, then it will begin to accelerate up the pressure gradient. And as it accelerates up the pressure gradient, it will consume potential energy and slow down until it's back in gradient balance. So what maintains the inflow in the presence of this outwards acceleration? Now this diagram has got a lot on it and may be a little bit small, but it is important because it contains the answer. So here's the radial flow and the azimuthal flow, and the remaining panels in the diagram are showing the terms of the budget equation. So this is the budget equation for azimuthal flow, this is the budget equation for radial flow. And we'll come across and we'll look at the radial flow first. So the first thing to see is this is the gradient wind residual. So this is the imbalance due to supergradient flow. Down near the surface where we have subgradient flow, we have an inwards acceleration, and this is actually the term that produces the cross-offs above flow near the surface. Then we have this layer of supergradient flow, which is associated with an outwards acceleration. And the magenta lines here are actually showing the zero lines in the radial flow, which are there and there. So just to help you orient yourself, these are the, this is the layer of outflow in here, this is the layer of inflow in here. And the other thing I should say is that the contours here are not linearly spaced because we're covering a very wide range of values. So we've got the zero contour, and then we've got plus or minus, that should be 1, 2, 4. So these are 1, 2, 4, 8, 16, up to 128 by 10 to the minus 4 metres squared, metres per second squared. So we've got an outwards acceleration here. What is balancing that outwards acceleration? Well, if we, and so we need to look for blue colours because we've got yellow-orange colours here. The first thing that's balancing it is vertical advection. So what is happening here is we're in the strong updraft. We've got an inflow maximum near the surface, and that inflow maximum is being lifted up to the level of the jet by the updraft. The other thing that is producing a inwards acceleration at the height of the jet is what I've labelled friction here, but perhaps it would have been more accurate to say this is the vertical diffusion. So what we see is that the vertical mixing is carrying the strong inflow near the surface up to the level of the jet. And together, those two terms are managing to maintain the inflow in the presence of the supergradient flow. The remaining term here is radial advection, so this is the UdUdR term. And that one is also producing an inwards acceleration near the radius of maximum winds. But it is largest near the surface because the inflow is largest near the surface, so the radial advection term is largest near the surface. It does have a role, but at the height of the jet, it is not as important as the friction and the vertical advection. Now, we'll also look at the budget for the azimuthal wind. Near the surface, we have friction, or vertical diffusion, is acting to weaken the azimuthal wind. So, predominantly, we're seeing a weakening of the wind. There's this very weak acceleration aloft, which I'll just return to in a second. We'll talk about it now. There's this very weak acceleration aloft because you have this, above the jet, you have a region where supergradient momentum is being diffused upwards and is accelerating the wind there. But mostly friction is weakening the azimuthal flow. Angular momentum advection we talked about, and in this case the zero contours of the angular momentum advection match the zero contours of the radial flow. So everywhere there's inflow, we have advection of angular momentum is tending to spin up the storm to produce positive acceleration. Everywhere where there's outflow, we've got the opposite sign. We've actually got the flow is being decelerated. And we have vertical advection, which is tending to carry weak azimuthal flow from the surface aloft and then strong azimuthal flow from the jet further aloft. And that term is somewhat smaller than the others. These, within the inflow layer, these two are actually fairly close to balancing. To first order, we have a balance between inwards advection of angular momentum and its destruction by friction. Now, you have, if you imagine the flow coming in here, it's as it ascends in the eyeball, it changes from inflow to outflow. And the strongest supergradient flow is very near, slightly within the top of the inflow layer. The flow ascends in the outwall, and as the flow comes in, it spins up, ascends in the eyewall, is supergradient near the top of the inflow layer, and then as it moves into the outflow layer, it accelerates outwards again. As it gets further from the surface, the factors that are managing to maintain the inflow become less important, and the flow starts to turn and go outwards in this red shading. And this red shading, this layer of outflow, the ascending eyewall air returns to gradient balance. It's very like a geostrophic adjustment situation. It's spun up, it's been supergradient, and then as it ascends further, the factors that are maintaining the inflow weaken. It moves out and comes back into gradient balance. So it's almost an inertial type of flow above the wind maximum. There's a lot to digest in this. It is in the 2001 paper, the Kepert and Long paper, so I encourage you to have a look at that. It's probably a good spot to give you the opportunity to ask questions if you want to.
Could you go back to the equations? Yes.
These ones. Okay?
I have a question. I wonder whether horizontal diffusion is negligible or not.
The horizontal diffusion in the model is negligible. Yes, and I didn't even bother writing it up there. In reality, there's probably some horizontal mixing due to eyewall mesovortices and the sort of processes that George Bryant and Richard Turner have written about recently. But from a boundary layer dynamics point of view, it's customary in the boundary layer to assume the aspect ratio is that it's very shallow and broad, and we neglect horizontal diffusion. I have run a model with more horizontal diffusion, but it doesn't change the results very much. It's a good question. Thank you. Sorry. There are 20 levels in here. The bottom level is at 10 metres, and the spacing increases with height until it reaches about 200 metres, and then it's held constant. So level 1 kilometre is approximately level 14 in the model. So it's very high vertical resolution.
This figure indicates that for the supergradient means vertical advection or something vertical transportation is very important.
Yes, the eyeball, vertical transport in the eyeball updraft is very important. And you can see that in these quite large values in the eyeball here. And again, quite large values in the eyeball here.
It means maybe indicate that the convection is
Yes, it potentially does, although in this model there's no buoyant convection.
I know.
Yeah. In an actual cyclone, the buoyant convection may very well be important as well.
This is not a question, but a comment.
Yes, that's good. I can have a little drink.
My comment is on the supergradient flow and particle here coming from this side, from here to here. So supergradient flow can be calculated between the absolute angular momentum between this side and this side. This side absolute momentum coming to this side, then additional wind blows.
Yes.
Then this is the amount of supergradient flow, I think.
That is a lot more than the amount of supergradient flow, because as the air particle comes in, a lot of the momentum. So here we have the angular momentum advection term. So this is the spin up due to the inward transport, but that is very close to being balanced with the angular momentum that is lost due to the surface. And if you count the contour intervals, this is the third contour, is at about 150 kilometres. Again, it's 1, 2, 3, third contour of the opposite side of 100 kilometres. So they don't exactly balance, but they are very close to being balanced. If you took air at 100 kilometres, which in this case is sitting at about 20 metres a second, and brought that air right in there, you could be seeing very, very strong supergradient flow, much more marked. And we see that in...
So the maximum force here in case without friction, in that case, my idea.
In that case, your idea would be correct. But of course, if there was no friction, there would be no subgradient flow near the surface, and there would be no inflow, because the inflow is largely driven by the residual near the surface. So what maintains the inflow in the presence of this outwards acceleration? It's mainly diffusion and advection of inflow from below, and plus a little bit of self-advection of the inflow. That's the UDR term. So a couple of things we can see from the model. You'll remember the slide I showed right at the beginning of Hurricane Guillermo, and we had the very different structure of the winds from between the three drop zones. So if you imagine taking the simulation and dropping drop zones, and we'll drop them either side of the radius of maximum wind. So one slightly inside and one slightly outside, and this is the radial and azimuthal winds that we would observe. The thick curves are inside the radius of maximum winds, the thin curves are slightly outside the radius of maximum winds. And we in fact see very different amounts of inflow and very different heights of the maximum, and somewhat different strengths of the maximum at the two positions. And that's somewhat reminiscent of the songs that were dropped on the northern eye wall, which were the black and the blue ones. The one dropped just outside shows quite a marked friction layer. The one that was dropped just inside in the black curve shows a relatively less friction layer. If we run the model in the same circumstance, but this time we've got the storm is translating rather than stationary, so the storm is moving to the left 5 metres a second. These are the Earth relative surface flow, the 10 metre flow. The azimuthal wind is a maximum in the right forward quadrant, and the inflow is a maximum to the right of the storm. And that's quite consistent with what we saw in the observations. Talk a bit more about why that is so. So there are the observations. Again, this one is moving to the northwest, you'll remember. Talk a little more about why that is so later. Actually, we'll do that now. So this is that same simulation again, and what I've plotted here is the Earth relative asymmetric flow, and we have the radial flow being a maximum towards the front of the storm, the azimuthal flow being a maximum to the right of the front of the storm, and we have an asymmetry in the updraft, that's favoured towards the front of the storm rather than being symmetric. What the remaining panels show here, this one is just the asymmetric component of the flow, and this is the wave number 1 component of the flow. And all I want you to look at for the moment with these is to notice that they are fairly similar, and that that the asymmetry is largely wave number 1, and we'll come back to that point in a little while. It's actually more useful to think of these in terms of the storm relative flows. So if I plot exactly the same data, but this time the winds have been calculated relative to the storm rather than relative to the Earth, we get a somewhat different looking picture. The maximum inflow is still towards the front of the storm, and but the maximum azimuthal storm relative wind has actually moved around to the left. This case is again moving from right to left. Again, the asymmetric and wave number 1 components are fairly similar. In this coordinate frame moving with the storm, it's easier to understand, at least in a qualitative sort of way, what's happening. Let's consider just the asymmetric flow. And we're moving, and we're in a coordinate system moving with the storm. So we are stationary, and the Earth's surface is going by underneath us. And the Earth's surface is moving past from left to right. So if you imagine an air parcel that's in the front of the storm, friction with the Earth's surface is going to tend to draw it in towards the storm. And an air parcel that's to the rear of the storm, friction with the Earth's surface is going to tend to take it away from the storm. And that, to first order, is the asymmetry that we're seeing here. We're seeing stronger inflow tending towards the front of the storm and stronger outflow tending towards the rear. And that's just the motion of the Earth going past underneath. If we look at the azimuthal flow, so we've got our basic circulation going around like this. To the right of the storm, the airflow is in the opposite direction to the Earth's surface. The Earth's surface is moving past in this direction. The air is going around this way. It's a Northern Hemisphere case. and as a result, we slow the azimuthal winds down. On the other side, the Earth's surface is going in the same direction as the wind, and so we speed the azimuthal winds up. So to first order, we've got something that's intuitively quite plausible in terms of the motion asymmetry. But there's actually more to it than that. And this is where it gets really interesting. The wind speed, the maximum inflow here is about 6 metres a second in this case. And yet the Earth's surface is moving at 5 metres a second. So we're actually getting more asymmetric inflow than can be directly accounted for just by the motion of the Earth's surface. So what's causing that? Let's think of it in terms of angular momentum advection. And although this is certainly not an inviscid situation, let's just pretend for the moment that angular momentum is conserved. Here we have strong inflow, which is going to import angular momentum and is going to produce an azimuthal acceleration. So as these air parcels are actually spiralling around, and as they come in, we've got a maximum in angular momentum advection here, which we would expect would give us our strongest swirling winds immediately downstream of them. Here the winds are most strongly swirling, and in fact are most strongly supergradient. We have the maximum wind on this side. And as a result, we have an outwards acceleration because we've got a positive gradient wind imbalance on this side of the storm. So this outward acceleration is going to tend to weaken the inflow, and as we move around to the rear of the storm, we find that we've in fact got net